that was a close one. I almost didn't record it. Okay. And so where we're at now, there is one more problem from this section focusing on logic puzzles, but I don't know. I'm gonna skip that for now. Maybe I'll put it on like the practice quiz on Friday or something like that. I would say, and you'll see the solutions when I post them later today or on Monday, whenever I end up posting them. Instead, I just want to go into section 1.3, which is on propositional equivalences, or another way of thinking about this is like logical equivalence. Before I get started, does anyone need the notes I passed out on Monday?
Notes you passed out on Monday, were those these?
Yeah, it's a same one.
Anyone else?
So I didn't really say it specifically, but we already have some experience with propositional equivalence from class on Monday. So what do I mean by this? So these propositional equivalences is going to be an important type of step used in mathematical argument, as we'll see throughout the semester and later on today. So really what's going on with these propositional equivalences is it's going to allow you to replace a statement with another statement with the same truth value, right? So we did this in class on Monday. For example, when we went through, oh, I'm not even on the right. Give me 1 second. So this is the first problem we did in class on Monday, right? We went through this truth table. And remember when we got to this step here, when we wanted to determine the truth value of not P implies not R, what we ended up doing instead is we recognized that this was the contrapositive of the following conditional statement, right? So we were already using propositional equivalence here in order to make our lives easier and make it easier to determine like what the truth value is going to be, right? So we're going to formalize what was done here to more propositional statements is really the goal for today. Right, so for example, earlier this week, and I guess last week, we saw that a conditional statement is logically equivalent to its contrapositive. So we'll see more examples of logical equivalence. Because of this, methods that produce propositions with the same truth value as a given compound proposition are going to be used extensively in the construction of mathematical arguments. I feel like I didn't need to say that. Again, this like last paragraph is kind of filler, I guess. Anyways, yeah, so before talking about, I guess, logical equivalence, let's go through the following definitions. So this definition is going to be pretty important in this class, and maybe you've heard it, maybe in like a philosophy class or something like that.
Or Miss you're gonna, sorry, I probably should have thought of and asked this earlier, but sorry, but I'm assuming you're gonna make an announcement or something to remind us about the Friday quiz.
Oh yeah, I'll send out an announcement, like a reminder about the quiz, probably tomorrow night. Maybe tomorrow afternoon. I shouldn't do it at night.
Review it, but I guess and then it's like tomorrow or something in preparation, right?
Yeah. Like I'll send out a reminder email. Yeah, and so the following definitions are going to be important in this class. So a compound proposition that is always true, no matter what the truth value is going to be called a tautology. So a tautology is a proposition that always outputs true. I don't think we've had exposure to this yet. We've come close with or, right? Like if you have two propositions and you or them together, they're all true except when both truth statements or truth values are false. So we'll look at an example of a tautology. And then the opposite is a contradiction. So a compound proposition that is always false is called a contradiction.
I believe there are the first usage of contradiction was actually not in math, but in like a historical example of an invincible shield or an unstoppable spear, like which if they were used against each other, which one would come out on top, you know?
Yeah, I think this stuff probably comes from like the ancient Greeks, if I had to guess. Like if you read like a Plato dialogue or something like that, he probably talks about like contradiction and tautology and things that are always true, things that are always false. And then I don't know if I'm ever going to use this term before, but a compound proposition that is neither a tautology nor a contradiction is called a contingency. Right, so just to get a little bit of practice with this idea of tautology and this idea of contradiction, we're going to look at the following example. And so what this example wants you to do is, given a single propositional variable p, it wants you to use the not, or, and the and logical operators to construct an example of a tautology and an example of a contradiction. Right, so we're only taking in one truth, like one proposition, and it wants us to use these operators to construct a tautology. Does anyone see how to do this? 1 second, I want to, yeah, can you try?
If P then not P, contradiction.
I don't know. Let's see. So if we had if P, then not P. Yeah, let's just look at the truth table of this. It is worth noting, I didn't include like the conditional, but I don't really care that much. Let's see what this ends up being. We can confirm or disconfirm whether or not it's going to be a contradiction or not. Yeah, so it should be a quick check. So this is either true. Oh, I need more columns. So this is true, true, false, false. This is going to be false. Oh, I guess I only needed 2 columns. It's early in the morning. Okay, that's my excuse. True. It isn't necessarily going to be. I mean, this is going to be. This is false. This is false. These last 2 statements are going to be true, though. Like if you have a false implies true, then that's going to end up being true. So this isn't going to be like a contradiction in this case, right? Like the only time this is going to be false, if like a conditional is going to be false if you have like true and then implies false. So this isn't necessarily an example of a tautology or a contradiction. It is an example of a contingency, though. It's either a tautology or a contradiction. Oh yeah, did you have a suggestion?
Something that I noticed when I mentioned contingency was it reminded me of how, despite now I'm not sure if I've heard of tautology before. I have heard of contingency used in other situations, such as the phrase contingency plan, you know?
Oh yeah, it's true. I mean, yeah, there's going to be uses for these words outside of this context. Yeah, do you have a idea?
Suggestion.
Mhm.
Could we do P or not P for the tautology?
Yeah, so that's what I was looking for this. So we have P or not P is going to be an example of a tautology. And it'll be easier to see. Like I'll do the truth table,
Does
but we'll look at like I'll put it in English as well. So this is P.
does not P imply P?
I think it will probably be the same as what we were just looking at least at the top of my head. Right, so if we were to combine these two via an or, so this is P or not P, right? So this is true, false. We have one true, so that means this is going to be true. And then we have false true because we have one true. It's going to be true, right? So no matter the output or no matter the input you have, the output is always going to end up being true. So this is an example of a tautology. Again, the important part is the fact that we have these 2 truths right here. If you wanted to think about like, what is this really saying in English? An example could be something like a ball is green or it is not green. This would be an example in English, right? So like either the ball is green or it's not green. Like these are the 2 possible cases, right? So like one of these has to end up being true and we're oring them together. So as long as one of these statements is true, the or is going to be true. So this is an example of a tautology.
For a contradiction, that makes me think for a contradiction, how about P and not P?
Yeah, exactly. So that's what I was looking for contradiction. So tautology, we were using or. To get contradiction, you can just change the or to an and. So let me, we're going to do a lot of truth tables today. So I'm just going to copy and paste. Change the or to an and. And in doing so, it's going to change our outputs because one of these is always going to end up being false, or each row is going to have at least one false. That means when we AND them together, it's always going to be false. Right, so this is kind of the quintessential example of a contradiction, right? So this is an example of a contradiction, and it's pretty much the phrase that we had before, except you change the or to an and. It's pretty much saying, like, an example of a contradiction is a ball is green and it is not green, which doesn't really make a lot of sense or really any sense at all. So if you change the word or to an and, you end up getting a contradiction. A ball is green and it is not green. It's a contradiction. Okay, any questions about this example? Okay, yeah, so these are words you just want to have in the back of your mind. Sometimes I'll use the word like this is a tautology or this is a contradiction, and I expect you to know what I mean. Okay, so now we're going to go into logical equivalences. First, or at least the first couple of examples we're going to go through, we're going to be determining logical equivalences via truth tables. But after we determine enough equations, eventually we'll determine, like, we'll look at this table, which is on page 7. And from there, you can kind of just, well, you're not going to remember every single one of these equations, but in the future, you can make arguments based on these equations without having to use a truth table at all, which will save you some time. It's a little bit more conceptually challenging, like remembering like what rules apply instead of just like using the logic of a truth table, but you can do it either way, I guess, on like the homework or on future quizzes or exams. Okay, so we kind of already talked about logical equivalences a little bit. So compound propositions that have the same truth values in all possible cases are called logically equivalent. Another way of stating it, I mean, I would remember it this way instead of the formal definition, but if you wanted to define logical equivalency in a more formal way, you can do it via the biconditional statement. So the compound propositions P and Q are called logically equivalent if P, if and only if Q is a tautology, right? So just as a reminder, like what was going on with the biconditional. So we looked at the biconditional in class, I think on Friday of last week. The biconditional outputs true as long as P and Q agree with one another. And so if P and Q, if and only if Q is a tautology, it must mean that P and Q agree with one another, right? Like P and Q are always going to be the same, right? So you can think about it this way: they have the same truth values, or more like mathematically, you can say that P, if and only Q, is a tautology. And so this is notation I exposed you to in class on Monday. But if two statements or propositions are equivalent, we write it as kind of like an equal sign with another horizontal bar. So if you see these 3 horizontal lines between 2 propositional statements, it means they're logically equivalent. So this is a common kind of problem that will show up, I guess, probably on Friday's quiz, on the homework as well, and then on the first exam, I'm going to ask you a problem like this as well. I don't know how many problems the first exam is going to be, but this is going to be one of them, except with like, you know, different signs, different like propositions, so on and so forth. And so at least at this point in time, the easiest way to determine 2 statements are logically equivalent is to just create a truth table, right? So a lot of the examples we're looking at in the beginning of class today are just going to be truth table problems, right? So we're going to make a truth table. And so we have 2 propositions, P and Q. So we have P, Q. We only have 2 propositions, so that means we're just going to have 4 rows. So this is true, true, false, false. And then this is, the Q is going to be true, false, true, false. For convenience, I'm going to copy and paste this because we're going to be using this again, I think, on the next example. And so what we want to do is we want to show that these 2 propositions have the same truth output. And so we can kind of go step by step like we were doing in class on Friday and Monday. So to determine the truth value of not P or Q, you can determine the truth value of P or Q first, and then you can apply the not to it. So we already know P or Q, this is going to be true, 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 and then false. And then if we apply the not to this proposition, all we're doing is just flipping these truth values to their opposite, right? So it's going to be false, 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 true. So if this is true, this one will be false, true, false, true, false, false, true. So you just flip everything to its opposite. Oops. And then in the interest of time, I'm just going to write out, we'll do other truth tables that are a little bit more interesting. So for this one, I'm just going to write out what this final one is going to look like. Right, what you could do is you could make a separate column for not P and a separate column for not Q, and then you can AND them together. But you can also just note, like if we're doing not P and not Q, like not P here is going to be false, not Q is going to be false. If we're ANDing them together, it's going to be false. Similarly, not P here is false, not Q is going to be true. If we AND them together, it's going to be false. The next row is pretty much the same idea, except the false. We have a false first and then a true. So this will be, after doing the not, this is going to be true, this will be false, and then we AND them together, so it's going to be false. And then finally, not P here is true, not Q here is true. If we AND them together, it's going to be true. You can also note, we know that P and Q is always going to be like true, false, false, false. If we apply like the not operators, it's really going to be all falses and then true for the last one. So however you want to do it, this is what it should end up being. And so we can determine that these two propositions are logically equivalent, because if you look at these last two columns we have, they have the exact same truth values, right? So this is like false, 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 true, true. And so what I was saying before, maybe this is unnecessary, but just as a point of illustration, if we considered the biconditional between these two statements, so if we considered not P or Q, if and only if not P and not Q, this is going to be a tautology, right? Because this is, these two agree with one another, these two agree with one another, these two agree with one another, these two agree with one another. So if you do the biconditional, because all their truth values agree, it's going to be a tautology. It's all trues across the board. Right, so we can confirm that the statements are logically equivalent. And unlike the quiz or exams or homeworks, you don't have to include this column. This was just for demonstration, right? I just wanted to illustrate, if you do the biconditional now, it's going to be a tautology, right? You can just really eyeball this and see that they're the same.
So we don't need that final column.
Yeah, you don't need the final column. It was just for demonstration. Any questions about this example? Okay, yeah, so that's what we're going to do for the next two examples as well. So this is actually an important law that holds for the not, or, and logical operators. This is one of the De Morgan's laws. So when you're thinking about these De Morgan laws, which are on the next page here, how to think about it is it provides you a way where if you have like the not operator and the and operator, it kind of tells you how the not is going to distribute over and or, right? So if we apply not to and, it's going to make it so we get an or, and then the negation applies to both propositions. And then conversely, if you apply the not operator to the or operator, then it's going to transform the or to an and again, you're going to distribute the not to both propositions, right? So these De Morgan laws are going to be very important in this class. You'll see later on when we start deriving other logical equivalences, but just remember, if you apply not to an and, it makes an or. If you apply not to an or, it makes it so you get an and, right? And then from there, it's just a matter of remembering you're negating all the propositions, right? The more practice you'll get, the more it'll become second nature applying these De Morgan laws. Okay, so that's something I wanted to mention. We'll make use of this in some other examples later today. For now, just keep it in the back of your head, I guess. Okay, so we'll go through some more examples here. So this next example, it wants you to show that P implies Q and not P or Q are logically equivalent to one another. This is what's called the conditional disjunction equivalence. So I'll do this one, and then the next example I'll have you work on your own for a couple of minutes. So I have the luxury of copying and pasting, so I'm just going to copy and paste the beginning of the truth table from before here. So let's first consider P, if P, then Q. And honestly, we already know what this should look like. So if you immediately just went into showing what the truth outputs of this proposition were, and you showed that it ends up being true, false, true, true, that would be sufficient as well. But just as a reminder, P implies Q has the following outputs. This is something that you should know at this point. We've done a couple of examples and explained why the outputs are going to be this way. And then let's just write out the not P. And then we're going to have not P or Q. So not P, again, is going to be false, false, true, true. And so now if you do not P or Q, right, we're considering these two columns. So if we do not P or Q, the first is going to be true. The second row is going to be false because we have false or false, which is the only way you can get false when oring. Then we have true, true. So true or true is true. And then the last row we have false or true, which is going to give you true. So again, all you need to do is just compare this column here with this column, and you'll see that the outputs are the same. And so this must mean that these two propositions are equivalent to one another. They're logically equivalent. So we're going to make use of this conditional disjunction equivalence in future examples. So this is like another one you want to keep in the back of your head. It turns out pretty much any logical statement can be expressed in terms of the not, or, and operators. So it's nice when you can rewrite a conditional in terms of nots and ors, right? It makes it so there's more things you can kind of interact. Okay, any questions about this example? And then what I was saying in the beginning is if you're doing this on an exam and you excluded this column and just had like these columns here, I would be fine because we kind of already know that P implies Q has these truth outputs, right? So if you're just like not P or Q has these truth outputs, which we know to be the same as like P implies Q, I'll take that as an answer as well because it's something we're already familiar with. Okay, so this next one, I mean, it's a little more tedious, but that's just life, I suppose. So this next example, it wants you to prove the distributive law of disjunction over conjunction. And so in English, maybe not English, in mathematical language, it's really asking you to do the following. So I want you to show that if you do P or Q and R, so we have three propositions here. It wants you to show that this is equivalent to doing P or Q and P or R. And so how to think about this or like remember this in a logical way is we're really distributing this or throughout this and, right? It's almost like this or is multiplication and this and is addition. And then we're kind of doing like the distribution from like algebra that you're familiar, right? So if you do like P or applied to this parentheses, it's really the same as like doing P or Q. And then the and then you have P or R. So it's like you're doing distribution via the or, okay? So spend a couple of minutes, maybe like 5 minutes or so going through this truth table. If you have any questions, I'll be around. I just want to first just make the truth table while you're working, or at least like set up the truth table while you're working. So.
Oh, the issue is this is Q bar. So this is the Q and this is the R. You know, it's easy to get something on worry.
Hope I did a good job with that we set up there.
Kind of like get lost.
Okay, thank you.
Yeah, we. But I mean, I'll post this week. Yeah, so what did you? I think they both have to be. Yeah, like I think, I'm trying to remember, I wrote this out a week ago. I think like it, I was thinking like, E is like the same as like A and like, B is the same as that B is and like, and then not B is like. Yeah, so it's like if B is true, that means like B has to be true as well. But then B is saying that they're different from one another, so that. Yeah. And then if A is an A, then B must be an A, which then says like if B is lying. If B is lying, then they have to be the same. Yeah, which means like you can't have like A's and like, or A's and A's and B's. Or A's and A's and B's. Because like, if B is lying and he's saying they're the opposite types, that must mean that it's. Yeah. Oh. I see. Okay, in the interest of time, I'm gonna go through this. I don't know if people are done or not.
I've been working around the U and the R, and I'm in the middle of working on the E or Q.
Yeah, I mean, when you have to do these like three propositions, it gets a little unwieldy. It can get hard to keep track of like where everything is. I might make a mistake myself, but yeah, so the first thing we want to do, when I was creating the truth table, I just kind of created a column for each individual, I guess, operation that we're performing. So for every or and every and, I made a separate column, and then eventually you can combine them together.
I've done Q or, I mean, Q and R, and I just finished E or Q.
Yeah, and yeah, there's a couple for here. So the first thing I'll do is like Q and R, because we have the Q and R that shows up here. So if we have Q and I'm gonna go through this a little bit quickly. So like both of these are true. We have one true, one false. So this is gonna be false. The next is gonna be false. That's gonna be false. This is gonna be true. This is gonna be false. This is going to be false. This is going to be false. Okay, any questions about this column?
Not about that column, since I.
Oh, we'll get to the other ones. We'll get to the other columns. Right now, let's just go one at a time. Okay, and then from here, what we're doing is we're taking P, this P here, and then we're ORing it with this column that we have here. And so with the OR, we should expect a lot more trues. Like it's not surprising we only had like 2 trues when we're doing the AND, because it's hard to get trues out of ANDs. And so if we're doing P or Q and R, so this is going to be true. We have true, false is going to be true. True, false is going to be true. True, false is going to be true. We have false, true is going to be true. And then the last 3 are going to be falses, because we have false, 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 false. So the last 3 are all going to be false. And so this is one of the propositions we're interested in, right? This is this proposition. So let's like, I don't know, for future reference, let's make sure we like, I don't know, like circle it or something, because it's what we want to compare this final column to. And ultimately, we should have that this final column has the same truth values as what we found in this column, right? So if they disagree with one another, it means that we've done something wrong along the way. And so all that's left now is finding these last three columns. Again, I'm going to go through this a little bit quickly. So we have P or Q. So this is going to be, well, you can just look, right? The only time where we're going to have false, false from P and Q are the last two rows. All the other rows have at least one true in them. So that means the truth table will look like this. Remember, the only time two ors are, or an or is going to be false is if both inputs are false. So it should look something like this. And then P or R, maybe it's a little bit harder to see. The only time where both P and R are false are the third to last row and then the last row. So those are the only times this column is going to be false. So let me mark those. And then the others are all going to be true. Okay. And then all that's left at this point is finding what the truth output or the output of this statement is going to be. So we have this and between these two ors, and now you just compare these two columns with one another. So we have true and true, true and true, true and true, true and true, true and true. And then the last three are all going to be false because we have at least one false. Well, this last row has two falses, but it doesn't matter. As long as you have one false, the output's going to be false when you're doing the and. So let's, I mean, you don't have to circle things, but let's just bring attention. These are the two columns we're comparing with one another. And you can see the first five outputs are all true, and the last three outputs are all false. The columns agree with one another, so these two statements are logically equivalent. So this one, it's a little bit tedious. On the exam, I'm going to probably ask you to do one that's a little bit shorter because it's, I mean, most of it, it's just like writing out all the columns and stuff like that. It's not like the most exciting problem of all time, but I wanted to do at least one example where we have three propositions. Any questions about this example? Yeah. I just look at kind of from smallest to largest, right? So, I mean, the order doesn't really, like you could do Q and R and then P or Q and then P or R, but I kind of try and do one statement at a time. So first I focused on this statement here. So we needed a P, a Q, and an R. Those are all like our basic propositions. And then here in the parentheses, we have a Q and R. So this is kind of like the next logical thing to build off of. So I was like, I'll make a column dedicated to Q and R. And then all that's left to complete this statement is then oring it with the P here. So you just have like the P or. And so it's kind of like going, I focus on the terms in parentheses first. And then once I was done with this statement, I moved on to this statement. So we have a P or Q. We have a P or R. And then the larger statement is just combining the two together via the and. I don't, it's like, it's a matter of practice, I suppose. And there's more than one way of like ordering these columns, right? You don't have to do it in that exact order, but does that make sense? Kind of just go from the smallest to the largest, like the least complicated to the most complicated. Yeah, question?
So you said if we don't get the same values, then we did something wrong along the way.
Yeah.
What columns were you talking about? Were you talking about the ones that you're circling?
Yeah, the ones that I've circled. What we wanted to do is we wanted to show that these two statements are logically equivalent to one another. So what that means is that these two columns, the column corresponding to this proposition and the column corresponding to this proposition, the outputs have to be the exact same. So you only have to care about this column and this column. Everything else was just building up to these columns. It's just kind of hard to see what the truth outputs are going to be if you don't have like all this build up. Like it's hard to eyeball this stuff, at least for me. Maybe some people can just like look at this and be like, it's like true, true, false, false. But not me, not me. Any other questions about this example? Okay, so you can do like a billion other truth tables, and in doing so, you can determine like a whole family of logical equivalences. I just listed them out in this table. Maybe I shouldn't say I listed. I copied and pasted from the book this table of logical equivalences that you can look at. I'm not going to read through all of them. Maybe just some important ones. Maybe I'll just look at I don't know, like this first one, right? If we're doing P and true, so like what this true means is that we're assuming that the output of this is always just going to be a 1, right? So if you do P and true, so again, T like denotes a compound proposition that is always true. This is really just going to be logically equivalent to whatever your P value is going to be. So if P is true, then this is going to output true. If P is false, if you do false and true, it's going to output false, which is the same as P. So that means these are logically equivalent. And then similarly, if you do P or false, it really depends on what the P value is going to be. Like if P is false, then you're going to output false. If P is true, this is going to output true. You can think about, I guess, the domination law as well. What else do I want to say? Some of the, I guess, the ones that are going to be important in future examples that we're looking at is if you apply the not operator to the not operator, they end up canceling out with one another. That should be pretty intuitive in that, like, if you do not true, it's like you go into not false, and then not false is true. So you get like the original statement back.
I've heard the word idempotent before.
Yeah, idempotent is like at least in math, something's idempotent if you have like e squared is equal to e. So what this is really saying is like if we think about this as being some sort of mathematical operation, it's like p squared is equal to p almost. Like 1, the number 1 is an idempotent. What else do I want to say? I want to go through another example, but I feel like I should say. Let's go through another example, and I'll talk a little bit more about these on Friday's class. So we'll end class with the following example. So this subsection focuses on constructing new logical equivalences. And so these logical equivalents in table 6 can be used to construct additional logical equivalences. I don't know if I want to read everything else out, right? It kind of makes sense. Like you can use these rules to construct new logical equivalences. And as a demonstration, there's the following example, right? So I don't know if I'm going to ask a problem like this on the exam. I would prefer you kind of have like whatever methods or tools you have available, like you're able to utilize them. So for this example, what I want you to do is I want you to show that not P implies Q and P and not Q are logically equivalent to one another without using a truth table. So on the exam, I don't think I'm going to ask you to do something without a truth table. Like if you're capable of showing something with a truth table, you should be able to do that. But for the purposes of kind of like demonstrating a new way of thinking about these things, I'm just going to say like do it without a truth table here. And so let's just start off by writing out the statement. So we have not P implies Q. And we want to create a chain of equivalences that ultimately ends with P and not Q. And so I guess I'll ask you, does anyone have an idea about where we can get started? We have this P implies Q. Is there anything we can do about this to make things maybe a little bit easier to work with?
I wonder, do we start by perhaps changing the arrow into one of the other symbols?
Yeah, it would be a good idea to change the arrow into ors and nots. Or yeah, go ahead. Yeah, exactly. I mean, this is what we showed on the previous page, right? We saw before that if P implies Q, this is logically equivalent to not P or Q. So we're going to make a substitution, right? So this statement is going to be equivalent to doing not and then doing not P or Q, right? So this is from, I guess, the first example on page 6. Yeah, so I don't have like a good notation. So this is like first example, page 6 here. And now we can use various other laws to simplify this further. Does anyone see where we can go from here? Like we have this not being applied to this parentheses. Does anyone see what the next step is going to be?
Is it from
maybe give like other people a chance. Yeah, do you wanna give it a shot?
Double negation rule.
We're gonna use the double negation law. There's a step that we need to do before doing the double negation law. Yeah. Yeah, do you know, yeah, we wanna do like we wanna distribute the not sign to this. Do you know what that's called? There's like a specific name for it.
Is it like factoring?
It starts with a D. It starts with a DE. Yeah, we want to use like De Morgan's laws here, right? So we can apply this not throughout this parentheses by using De Morgan's laws right here, right? So this is the same thing as doing really we're doing like not P, and then this is going to become an and then this is going to become not Q. And now we can use the double negation law. And in doing the double negation law, this not P is going to become P. And then, I mean, we'll leave like the not Q. Right? And so this is the statement we wanted to arrive at. So let me label. So this was using De Morgan's laws. And then this is the double negation. I should have a better system for, I guess, like writing out where these equalities come from, but hopefully it makes some sense. Any questions about this example? Okay, so I think the first 10 minutes of class on Friday, I'll go through these last two examples. The next 20 minutes, I guess there'll be like a practice quiz you can work on in groups. And then the last 20 minutes, there'll be a quiz, the quiz itself, okay? If you have any questions, feel free to reach out to me, and I'll make an announcement about the quiz on Thursday so you remember to study for it.
When we're studying the law, do you want us to like memorize them, or are we gonna be given?
Well, I think, well, on the exam, I'll allow you an index card. But I think I should probably specify, I think when I do an exam review, I'm gonna specify the ones you should know. Like remembering this whole, I'm not gonna ask you to remember this whole thing, is what I'm getting at.
I think I was kind of in the days when we first started the truth tables. So the only thing that I'm kind of confused on, like, once I get these values, I know how to get the next values, but how do you know how to just like start?
Yeah, there's kind of like a system to it. I talked about it a little, like for a couple minutes before, but like it depends on the number of variables you have. Like the idea is, like depending, the number of rows you have depends on the number of propositions. So we had 3 propositions. So that means there's going to be 2 to the 3 many rows, or like 8 rows. And like if we had 2 propositions, that means we have 2 squared, so it's like 4 rows.
Okay,
And then from here, the first column, it's kind of like half of them are going to be trues, the next half are going to be false. So if we had like 16 rows, instead would be like 8 trues and then 8 falses, they can disconnect it. And then the next one is going to be, it's kind of hard to like formalize it, but this is like true, true, false, false, true, true, false, false. Like it alternates in 2s. So it's like alternates in 4s, alternates in 2s, and then this alternates by 1. It's like true, false, true, false, true, false.
will we ever have a situation where we have a like?
I'm not gonna do that to you.
Okay.
Yeah, it'd be too annoying.
Okay,
I think.
thank you.
Is it's having trouble disconnecting?
I had trouble connecting it. Yeah, so this is
Are you about to go to the?
yeah, it's kind of a pain.
So I just joined, but you said we have a quiz Friday, do you know, is it everything from the first day till now?
Yeah, so it'll be covering, it probably won't be going over what we just did. Like on the quiz, I'm not gonna ask you to do this without like a truth table. Logical equivalence, but what's that?
Is it more confusing?
It's on Canvas as well, so you can find the notes.
Is it possible for P and P to exist in the same universe?
I mean, not really. I mean, that's like it's like the contradiction. I mean, if you're thinking in terms of things that are concrete,
Okay.
not really, in the sense that like you can't have something that, I mean, we saw like
It's a
the,
contradiction.
Hmm?
It's a contradiction at a sort of level.
I don't know at lower level is saying.
It's, you know what?
Well, yeah, it's like I don't know, it's kind of a hard question. Well, in the sense, I'm just trying to think of like in the material world, like you can't have something that has a quality and doesn't have that quality at the same time. Right? Like you can't, like is something a painting and not a painting, something like is something water but not water? I don't know.
I mean, I guess that's a question for later.
Yeah, it's like in the realm of philosophy.